Great, it's recording now. Today we're going to talk about section 4.9, Newton's method. Okay, so basically now that we know derivatives, we're going to look at a very nice application of derivatives, which is called Newton's method, in honor to Isaac Newton, who was the one who developed this nice method. Now, very often in mathematics, we encounter this situation. We have to solve for x an equation that looks like this, right? F of x equals 0, an equation of this form. Now, it is difficult in general to solve equations of this form, right? And even in some cases, impossible to solve these equations explicitly, right? But however, with this Newton's method, we will always be able to approximate the solutions for this equation as much as we wish, as long as we can take the derivative of its f of x, okay? The derivative. So Newton figured out that if you apply this iteration, xn plus 1 equal xn minus f of xn over f prime derivative, right? Apply at xn. If you apply this iteration repeatedly, eventually you will get such a great approximation to the 0 of this f of x that you will just stop and will say, aha, I got a good approximation, that's enough, right? Yeah, but how he figured this out, let me explain, right? Welcome, Julian. How are you today? Everything good? We just started with Newton's method, which is the last section that we have to cover before we go into the preparation for our exam 3, right? Okay, so I was saying that Newton's method is a nice application of derivatives, and it's basically this algorithm, right? What you see here, right? And it's based on the following idea, right? Welcome, Jason. We just started with Newton's method, right? Application of derivative again. Remember, guys, I told you in calculus, the hero is the derivative, because the derivative helps you to do basically everything that you have to do in calculus, right? So this is one more application of derivatives. Okay, so as I was saying, right, Newton figured out that by applying this algorithm repeatedly, right, we can get good approximations to the zeros of this type of functions, right? F of x equals 0, as long as you can take derivatives. Now, what's the idea behind this formula, right? How he kind of figured this out? Well, imagine, right? Imagine that the graph of this f of x is this curve in general, right? In general, and this curve. And imagine that this curve meets the x-axis at this x with this asterisk on the top. Let's call it x star, right? This is the actual 0 of f of x, right? And let's try to figure out how we can find this 0 using derivatives. Well, Newton figured out this. He said, start with a guess, right? A guess for the 0 of f of x. Let's say that guess is x0, some guess. Then he said, raise a perpendicular at x0, meet the graph. At this point, draw the tangent line, right? The tangent line. And pay attention to where the tangent line intersects the x-axis. You can see that that happens here at x1, right? x1. But now notice, x1 compared to x0 is a better approximation for the actual 0 of f of x, right? Which is this x star, right? Because it's closer now, right? Compared to x0. Okay. And then Newton suggested, once you get x1, in order to improve x1, do what I suggested again, right? So raise a perpendicular, meet the graph, draw the tangent line, and pay attention to where the tangent line meets the x-axis. Now that is happening at x2, right? And you can clearly see now that x2 compared to x1 is a better approximation for the 0 of f of x, because now it's even closer to x star, right? And he said, if you continue doing this, right, again, another perpendicular, another tangent line, look, the next tangent line probably will be very, very close to X star, right? And if you continue doing that, you're going to be so close to X star that it will not make sense to repeat the process again, right? And at that point, you stop. You stop, right? So this is the idea behind this formula, right? And you may say, Professor, you said that derivatives are used. How come? Well, notice, right, that the tangent line has a slope, and that slope is controlled by the derivative, right? In order to find this point algebraically, you're supposed to find the equation of this tangent line, and for that, you use the derivative, right? But everything worked out leads to this formula, right? That we're going to use, right, directly, right? So, but this is kind of the background, the main idea behind this formula, right? Yeah, great. So now, let me explain to you how this method works numerically, right, with an example. Example 1, we're going to start as usual, right, with a very, very basic example, right? Says, write the formula for Newton's method and use the given initial approximation to compute the approximations x1 and x2 round to 6 decimal places, okay? So they are giving you some f of x here, which is equal to x squared minus 20, and they are giving you a guess. They are guessing x0 equal 5 is 0 of the equation f of x equals 0, right? Is 0 of this f of x, a root of x, right? So how you start? Well, start by writing out the formula for Newton's method, right? Which is this. X, X, let me just write it again. Sorry, since no, let's just close it and open it again. X, N, sorry. Xn, good, plus 1 is equal to xn plus the function f evaluated at xn divided by the derivative of f evaluated at xn. To put it simple, guys, out of xn, the previous guess, you get the next guess, xn plus 1, right? This is the general formula. Great. Now, to put it simple, if I am looking for x1, then I have to use the previous x0 plus f evaluated at x0 over the derivative of f evaluated at x0, right? Yeah. But what is x0? Well, x0 is given. You can see it here, right? They give it to you. They gave you the first guess, 5, right? The number 5. All right, so we say, okay, then x1 will be equal to x0, which is given 5, plus my function evaluated at 5 over the derivative of my function evaluated at 5, right? We're gonna use f, the function, and its derivative f prime. So let's write out here what is f and what is f prime. F of x is this formula, right? X squared minus 20. And the derivative of f of x is just 2x minus 0, nothing, right? 2x, right? We're going to use these two guys repeatedly. So let's compute this guy, right? x1 first. What is x1? Well, x1 will be equal to what? I am going to use my Desmos scientific calculator and do that computation. I will show you how. Look, I need to do this computation, 5 plus, then this fraction comes up, right? This fraction comes up, so I recommend that you do this. Click here on fraction. On the numerator, I am going to do the evaluation of this function at 5, but the function is x squared minus 20. So I have to do within parentheses 5 squared minus 20, right? Minus 20. That's the evaluation of the function on the numerator, always. On the denominator, I will do the evaluation of the derivative at 5, right? The derivative is this twice x. So the evaluation of the derivative of 5 will be 2 times 5, right? 2 times 5. All right. So don't forget this is minus. I wrote plus there for some reason it's minus. It's minus. Sorry. This guy is just minus. I will fix it here. It's minus, right? I will do it again, don't worry. So this is minus. So the formula, right? Minus. Remember? Minus. Okay, great. So we're after x1, right? So we said use your calculator. The evaluation of 5 was this, right there. And I end up with this value, 4.5, right? 4.5. First iteration is equal to 4.5. Let's write it out here. Let's put this down for a moment. 4.5. So 4.5 here. This is the first iteration, right? And notice that compared to our first guess 5, is kind of better, right? In the sense that it will be closer to the actual root or the actual 0 of this f of x. All right. But now that's x1, right? Now they want x2 also, right? Besides x1, they say they want x2, right? And they say approximate to 6 decimal places. So x2 now, what will be x2? X2 will be x1, the previous, minus f evaluated at x1 divided by f prime at x1, right? So now x2 then will be equal to what? The x1 that we got here, 4.5, minus the evaluation at 4.5, right? Over the derivative evaluated at 4.5, right? 4.5. But now I have this Desmos computation handy here because notice, guys, that I'm doing the evaluation again, but now it's all about changing this 5 for a 4.5, right? The same evaluation, but instead of evaluating at 5, I'm evaluating now at 4.5. So work efficiently, guys. You don't need to retype this whole thing, right? Instead, just change this for 4.5, right? That's why I put the parentheses there, right? Now, look at what we got now. 4.472222, which rounded to 6 decimal places is just this, right? Up to 6 decimal places is this. Very good. All right. So let me write this out. Okay. So x2 will be, I close this, x2 will be finally this value. 4.47222, right? To 6 decimal places. So you got a sense of this method, guys, then? Look, it's this formula, right, that has to be applied repeatedly, right? Repeatedly. You find the first output, and then for the next iteration, the first output becomes the input, right? Becomes the input, right? And you get a new value. And eventually, the sequence of x1s, x2s, x3s, x4, you continue, right, will converge to some number, right? And at that point, you stop, you say, we're done. We found a good approximation for 1, 0 or solution to this equation f of x equals 0, right? That's how Newton's methods work. All right, this was a very basic example, right? It dealt with a quadratic function. You may say, Professor, but this quadratic function, I can solve it using the quadratic formula, just isolating x squared, taking square root, true, right? But it's just to illustrate the Newton's method. Now, on example 2, let's take a complicated equation. Look, x squared minus 4 cosine of x, right? There is no quadratic formula here, right? There is no explicit formula to solve this equation f of x equals 0 here, right? But however, Newton's method will give us an algorithm to approximate one solution for this equation f of x equals 0, right? one zero, one root of f of x can be found. And they are giving us a guess, x0 equal minus 3 to start with, right? To start with. Yeah, it's a numerical method, guys. They will always give you a first guess, and you just have to continue, right? You have to continue. All right, says for the given function, f, an initial approximation, x0 equal negative 3, use Newton's method to approximate a root of f, right? A root of f. Stop calculating approximations when two successive approximations agree to 5 digits to the right of the decimal point after rounding. Show your work by making a table. Okay, so let's do that, right? Let's do that now. Again, it all starts by identifying our guess, right? Our first guess is this, x0 equal negative 3, right? And we start by writing out the formula for Newton's method, right? Which is this, xn plus 1 is equal to xn minus f of xn over f prime of xn, right? With xn, you get the next xn plus 1. That's the whole idea. Now, I'm going to start by getting x1 as usual, right? X1 will be equal to what? Will be the previous x0, right? The initial guess in this case, right? Minus f evaluated at x0 divided by the derivative evaluated at x0, right? This is what it is. Now I'm going to use f, I'm going to use the derivative. So let me write this out here clearly. F of x is equal to this guy, x squared minus 4 times cosine of x, right? And its derivative, f prime of x, will be equal to what? Derivative of x squared twice x minus 4 constant. Derivative of cosine, remember, is minus sine of x, right? And simplifying this derivative, you can see that minus and minus is plus. So we will get this guy, right? 4 sine of x. Very good. So this is the derivative in simplified form. This is the function. So now I have to use the function and the derivative repeatedly, right? Repeatedly. Okay, so let's do that together. So this guy then will become what? This guy will become x0, but x0 is negative 3, right? Negative 3 plus what? Plus minus. Let's be careful here. Minus the evaluation of the function at negative 3, right? Divided by the derivative of negative 3, right? This is what we're gonna do. But now, let's do it in our calculator, right? In our scientific calculator, Desmos. Scientific calculator. Okay, so we gotta start with negative 3 first, right? Negative 3 first. Let's put it here so we can see the function. All right, negative 3 first, then minus, right? Then advice, since we are going to deal with a fraction here, use this fraction form, right? Fraction form. On the numerator, you evaluate at f, right? So evaluation at negative 3 of this function. So that is going to be, I'm going to use parentheses because I'm replacing, so substitute a negative number, right? Negative 3 is squared, negative 3 squared minus 4 times the cosine of negative 3, right? Negative 3. Don't forget to work in radians, right? Radians here, click in radians here. Yeah, very good. That's the numerator. What's the denominator? The evaluation at the derivative, right? But the derivative in simplified form is this, right? So that will be 2 times x, but x is supposed to be negative 3, right? I'm already at negative 3. So minus 3 here, close parentheses, plus 4 times, now sine of parentheses, right? Negative 3, right? Negative 3. And again, make sure you're working in radians, right? All that gives you this computation, right? This value, minus 1.0257, right? They are asking you to round your work to how many decimal places? 5 digits, right? 5 digits. So we're gonna do a rounding to 5 decimal places. So we're gonna take all this for 1, 2, 3, 4, 5, up to there, right? This is what I'm gonna write down here, okay? So I'm gonna put this down for a moment. I'm not gonna close it, just put it down. I will tell you why. And I'm gonna write here my result, minus 1.02574, right? That's what we got when we round this to 5 decimal places. Now, I'm supposed to get x2, right? But what is x2? X2 is gonna be the previous x1 minus the evaluation of your function at x1, right? Divided by the derivative evaluated at x1, right? So basically, I gotta take this output and consider that as my input for the next iteration, right? So this is how this works. This here minus the function evaluated at this guy, right? And all that divided by the derivative of f evaluated at this guy, 0.2574, right? This type of computations, this type of algorithms are called iterative methods, right? Because it's all about the result becoming the new input and keep doing this again and again and again, right? Yeah, great. But what is this equal to? Well, in order to facilitate the computation of these guys, remember I put these Desmos computations down, right? I kept it. Why did you keep it, Professor? Because look at this. I did this computation with the input value -3. I gotta do this again, but now with this new input value, right? So what I do is just I simply replace this -3 with this value, right? So it's gonna be minus 1.02574, right? 74. And then I simply copy and paste. Look, copy and paste. These are going to be numbers with a lot of digits, right? It will be annoying to do this again and again, right? So just copy and paste. You see carefully, right? I'm replacing this -3 and copying and pasting the new input, which is this guy, right? Yeah. Copy and paste your new input value here, right? And then we do this efficiently, right? So, now look, the new output value is this, right? We're gonna write that down. I write that down. That's gonna be x2. They want you to round this to 5 decimal places. So you go up to here, right? 2 to 5, up to there, right? This is what we're gonna write here, right? Very good. Okay, great. So, and now don't close this, just put it down for a moment, right? Because we're gonna reuse it next. All right, so I'm gonna write the result of this was negative 1.21246, right? Rounded to 5 decimal places. Great. Now we have to do this again, right? Eventually, you will see that they will converge to some number. You will see it. So now x3, right? x3 here, x3 equal what? The previous x2, right? Minus f evaluated at x2 divided by the derivative, right? Derivative evaluated at x2, right? Good. But what is this? Well, now x2 is this guy, right? So I gotta evaluate the same formula, right? Same formula this, but at this value. So for that, I kept my previous computation, right? So it's all about changing these guys, right? All these guys within parentheses for this new value now, right? With this new value here, right? So that's what I'm gonna do now. So I'm gonna change this for minus 1.21246, right? And then I just copy and paste this to be efficient, right? Copy and paste. Control, Command C, Command V, right? Copy and paste. Just do this carefully. Or you can retype the whole thing, right? It doesn't matter really, but just to be efficient, I'm using copy and paste. It's the same formula, right? Yeah, great. Now I get this new value, right? You see this new value. And this new value now must be written here, right? Yeah, here. So I'm gonna put this down for a moment, right? All I did right now was this, right? Minus 1.21246 minus f of negative 1.21246 divided by the derivative of this guy, right? The output became the input for the new iteration, right? So yeah. And as a result, I got this guy, right? Minus 1.20157, right? So that, professor, yeah, this is what we got, right? This guy is here, rounded to 5 decimal places. They will tell you how many decimals they want for the rounding, right? So it was 5 decimal places, so we went up to there. Great. That is x3, right? X3. You can see that somehow, look, up to 1 digit is kind of repeating itself already. So it's close to the level where this would get stabilized. So one more time, x4. Let's see what happened at x4. x4 will be the previous x3 minus evaluation at x3 divided by the derivative at x3, right? But this will be equal to what? This guy minus 1.20157 minus the evaluation at this guy, right? Minus 1.20157, right? All over the derivative of your function evaluated at that number, right? 57. Now we're going to compute this with our calculator. So let's bring back our Desmos calculator is here. Right, for some reason I closed it, but doesn't matter, right? Let's do it again. Let's minus 1.20157, right? Minus the evaluation of the function. The evaluation of the function, for that I need a fraction form, right? Evaluation of the function is this, right? So you can just do this square minus 1.20157 square. Square minus 4 times cosine of this guy, right? Minus 1.20157, right? Yeah, great. This is on the numerator of the function, and on the denominator you have to write the derivative, this guy, right? This guy. Twice the value of x, that value of x is minus 1.20157, right? Close parentheses, plus 4 times the sine of this guy in radians, right? Sine of this guy, negative 1.20157 in radians, right? Yeah. And to avoid retyping, you can just copy and paste, keeping the previous computation, right? Yeah, now in radians, remember, in radians. Now, look at this. Now you can see that this guy has become rounded to 5 decimal places, negative 1.2015. Since this is 8, this has to be 4, right? 4 here, 4. So let's do that, 4. So minus, I close it again, but 1.20154, right? Yeah, this is this. And we are very close to the end, because notice how now, before these 2 was repeated, but now 3 decimal places are repeated. It's getting stabilized, right? So probably will take just one more time to do it, and then we will stop. X5 will be the previous x4 minus f of x4 divided by the derivative evaluated at x4, right? Which is what? This guy, 1.20154 minus the function evaluated at this guy, 4, over the derivative of the function evaluated at negative 1.20154, right? Great. Let's see what we get now. All right, going to the Desmos calculator. We do minus 1.20154, right? minus, minus, and here fraction, right? I'm gonna just copy and paste this. Okay, so here I have to get the function square, right? So I'm gonna copy my value there, square, right? Minus 4 times cosine of x, right? Cosine of pasting, right? The input value. And on the bottom, the derivative, twice x, twice, within parentheses, I paste my input value, right? And then plus 4 times sine of base here. That's it, right? Yeah, and don't forget the computation must be done in radians, right? Look at this, guys. Look, isn't it the same as this? Exactly the same. When you round it to 5 decimal places, look, when you round this number to 5 decimal places, the 3 becomes 4, right? So exactly the same as this, right? Exactly the same as the previous computation. That is good news, guys, because then at that point you just stop. You just stop, right? When the output gets repeated, right? In this case, rounded up to 5 decimal places, you say, this is an important point because this and this up to 5 decimal places are exactly the same, right? Same, right? Same. Then stop, right? Stop right there. You're done. This is the best approximation that you could have gotten up to 5 decimal places, right? This is supposed to be the zero of f of x, right? It took 5 iterations, right? Sometimes may take 3 iterations, sometimes 4 iterations, sometimes 5. Depends on the function, right? Depends on the function. But this is how you use Newton's method. Okay. And now they talk about a table there, right? A table there. How do you construct this table? Well, the table can be constructed, let's say this way. You put n here, xn here, and you can do something like this, perhaps, right? N0, for N0, X0 is what? The original guess, right? Which was this guy. X0 was -3, right? -3 original guess, right? -3. Then for X1, we improve, right? For X1, we improve. We got this guy, minus 1.02574, right? For X2, we improve to this, right? So negative 1.21246, right? X3, we improve. We got this guy, minus 1.20157, right? And you notice how these digits start repeating themselves. X4, we got this guy, and it's there where we got a repetition up to 5 decimal places, right? Because notice X5 is exactly the same. And that is the reason why we stop, right? We stop and we say, we stop here, right? Stop because they're the same, right? Same values. Great, that's it, right? Okay, guys, it's just iterative methods, right? You repeat the algorithm, and then until you get this repetition, until the output values get stabilized, and then you stop. All right, I'm gonna ask you to solve one of these, and then we'll do something else. This one is precisely the one that I just did, right? As you can see, all right? So the table matches completely with this, right? That is why the answer should be this A, right? This. Great, but now let me work on something. Let's erase this and let's work on this then. Try to do this. We'll do it from scratch so we can all see what's going on there. Let's try to do this, okay? Together, number 2. I will give you the hints, okay? So we'll do this together. So, let's see. Start by writing out your x n plus 1 as xn minus f of xn over f prime of xn, right? And they give you the first guess is 4. So start with 4. Start with this computation. X1 should be equal to x0 minus f of x0 over the derivative at x0, which translates itself as x0 being 4 minus f evaluated at 4 over the derivative of the function evaluated at 4, right? F of x, the function, is this x squared minus 3 square root of x. The derivative of this function, remember, is this twice x here. And the derivative of this part will be 3 on the top. The derivative of the square root of x, remember, is twice the square root of x, right? So use this for a derivative, okay? So use this for the function, use this for the derivative. Try to get these values, x1, x2, x3, right? And eventually they will get stabilized when you notice that stop, and then identify the table that corresponds to that, right? Yeah, go ahead, try, guys. Mm-hmm. Mm-hmm. Yeah, and one of the tables will reflect the work, right? Yeah, one of those tables. Mm-hmm. Yeah, this and sometimes students ask me, how, professor, you went from here to here? Let me write here, recall the derivative with respect to x of a square root of x is just this, right? 1 over twice the square root of x. This is what I use here. Yeah, some students figure this out. Very good, Inosa. Very good, very good. Excellent. Yeah. Yeah, very, very good. We're okay there. Yeah, let's compute this. This part, this Newton's method is just computational, guys. It's the last part that we need to cover, so we can go ahead reviewing our stuff for exam 3, right? Yeah, so let's do the first computation, right? What will be the first computation? And let's try to do it efficiently using our Desmos calculator, using copying and pasting, right? So I will show you. So x1, what will be x1 using Newton's method here? Well, let's bring out the calculator, right? Yeah, so I don't need this anymore, right? So let's open a new one. Okay, so I need first to do 4 minus what? Fraction here, right? So pick this for fraction form, and I need to do the evaluation first at this function, right? I need to do 4, which I'm going to write within parentheses. So later we can use this form for the other computations, right? Minus 3 times a square root of here, square root of 4, right? 4. This is the evaluation at 4, right? On the denominator, I have to do the evaluation at the derivative. So twice 4, minus, notice there is another fraction here. So again, fraction here, fraction. 3 divided by 2 a square root of 4, right? 4. Yeah, and what I get is the following. Let me see. Let me check, double check everything. Yeah, 2.62, right? Oh, I forget the -1 here. Sorry, guys. There's a -1 there, right? For the f of x. So this is -1. So this one -1. I will write it here. Sorry. this had a -1 there. I didn't. The derivative will be the same, but this guy is -1. So this is what we get. Yeah, that's this one was -1 here. The function, right? Yeah, correct. Yeah, very good, very good. Yeah, then it will change a little bit. Yeah. So now on the Desmos, I have here the evaluation of the function here, the derivative here. Now this, right? Yeah, very good, guys. Yeah, yeah, Julian figured it out. Excellent, excellent, Julian. Excellent, very good, very good. Yeah. So now this is the first computation, right? 2.75862. They are rounding to 1, 2, 3, 4, 5 decimal places. So I'm gonna go up to 5 decimal places here, up to here, right? I'm gonna write out 2.75862. Okay. Great. And I'm gonna just put this down because I'm gonna use this, right? We're gonna use that. So this first computation, I hope everybody agrees, that is equal to 2.75. 2.75 A62. A62. Great. This is the first one, X1, right? Now for X2 is going to be the previous X1 minus F evaluated at X1 over the derivative evaluated at X1, right? Yeah, so it's going to be the same computation, but now with this guy as the input. So it's going to be this guy, 2.75862 minus the function evaluated at this 2.75862 divided by the derivative evaluated at 2.75862, right? Very good. But that I can efficiently do it just by bringing back what I had before, right? Before I had this. So all I gotta do is replace this 4 by this new number, right? With this 2.75862, right? And then I can even copy and paste that number to simplify my work, right? I copy, Command C, and then here, Command B, right? That's the new input. The new input appears again here, so Command B. And the new input appears here again, Command B. And the new input appears here again, Command B, right? Let's work efficiently, guys. Yeah, I get this new number, 2.40595, rounded to 5 decimal places, right? Follow, guys? Yeah, this guy. This is a new value. So that will go. Now, I'm not going to close this, right? So I don't want to type it in. I just put it down here, down, right? So let's write our new answer here as 2 point here, 2.405, 40595, right? 95. This is X2, right? Then we are supposed to compute X3, right? As the previous X2 minus F evaluated at X2 divided by the derivative evaluated at X2, right? At X2, that's how it works. Now, this will be this new guy, 2.40595 minus evaluation at this guy, 2.40595 divided by the derivative of the function evaluated at this guy, right? 2.40595, right? And let's see what we get. For that, I bring back my previous computation, and all I do is I change this number for the new input, right? For this. So let's just change this and then just copy and paste. 2.40595, right? 40595. And now to simplify my work, I'm gonna copy this and paste it every time this appears right here. Again, here, another. Paste it, right? It's work efficiently, right? You can write it out this, right? But it's kind of long and takes time, right? So instead, just copy and paste. Very good. Now I get this new number, 2.37077, right? rounding to 5 decimal places again, right? It's a new. Now I just put this down, right? Don't close it, just put it down for a moment. Write your result here for x3, 2.37077, right? Rounded to 5 decimal places, right? And notice that little by little, we are headed somewhere, right? It's not noticeable yet, but probably soon. X4 now. X4 now. Someone wrote in the chat. No, the note is asking, it would take always 3 times. Sometimes it takes 4 times, sometimes 5 times, but it's coming close. It's coming close. Yeah, we will see, right? Yeah, but depends on the function. So some functions, they converge quicker than others. Yeah, but depends. So let's see this one, right? X4 will be X3, the previous, minus the evaluation at X3, divided by the evaluation of the derivative at X3, right? Good. So we take this guy. This is our new input, right? The output of the previous iteration becomes the input of the new iteration, right? Yeah, so this is this. Yeah, these are called in mathematics iterative methods, right? If you are headed or studying computer science, you're going to use these methods a lot because this is actually what computers do to solve equations, right? Yeah. Great. This. Now we're going to do this, right? So I already have the structure here, right? Because I computed this before. It's all about changing out these guys for the new output value, right? This, which is the input for this function, right? 2.3 now. I need to change this for 2.370777, right? And then I just copy and paste, right? Just to simplify my life. Copy, paste here. Carefully. Here, paste. Paste here. And then we should have our new output value. 2.3704093. 2.37041, right? There you go. So let's write it out, right? Let's just put this down for a moment, right? Let's write out our result. Our result will be now 2.37041 rounded, right? Notice the repetition now of 2 digits, 3 digits, right? So it's good news, right? It's almost the same, right? So it's coming up, the stabilization of this iteration. So one more time, x5 be the previous x4 minus f of x4 over derivative evaluated at x4, right? So basically we are taking this output and making this our input for the next iteration, right? So this guy is here minus the function evaluated at this guy 37041. And I see more students are posting answers, right? It is an iterative method, numerical method algorithm, right? So let's see what this gives us. Let me read the comments on the chat. Yeah. Yeah, Dinosa, you have a question? How do we know when to stop? How do we know when to stop? It's coming up next, Dinosa. You will see. Look, if I compute this whole thing, if I bring back my previous computation, now I have to change this input by this guy, right? By the new guy, which is this 2.37041, right? I copy and paste this, right? Command C, Command V, right? I'm doing this in a Mac computer. In Windows computer, there must be another way to copy and paste, right? But it's similar, right? So it's copy and paste. So you avoid writing this out again, right? Okay, here. And here is the answer, Dinosa, for your question. Dinosa, it's a great question, right? When do we stop? Look at this. Look, Dinosa. When I get this guy, isn't it true that this guy rounded to 5 decimal places, exactly the same as this? Exactly the same, right? Look, 2.3704. And because of the rounding, this 0 becomes 1. So exactly the same. There you stop. There you stop, right? That's it. You put down. So this guy should be 2.3701 right? Same, right? Same. So it means that you stop, then stop. Because the idea is that if you continue doing this, it will be repeated itself, right? So it doesn't make sense to continue, right? That's it. You follow, guys? Yeah, let me close this, right? Finally, we finish the computations. Now, so is it clear, Dinosa, now why or when you stop? Yeah, you got it. Yeah, thank you, very good. Yeah, when the numbers repeat themselves up to some number of decimals, because they said to you, right, do this using 1, 2, 3, 4, 5 decimal places, right? How do you know, Professor? Because look at the tables, right? All of them have 5 decimals. No 6, no 7, right? Just 5. So you follow that. So when you get to the stabilization, you stop. And then the table, of course, will be the one showing all these guys, right? All these guys. And that is table, I think, C, right? C. Very good. Very good. This one, right? Look, notice this one starts with 4, our first guess. Then this number here, right? Which is this guy, right? Then this guy, right? Then this guy, right? Then the stabilization group. This guy equal to this guy. And then it's when we stop, right? You follow, guys? Yeah. More questions here. Let's see. Yeah. 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 Dinos is asking me, is this a long question going to be on the exam 3? I think one question will deal with Newton's method, okay? But don't get freaked out, guys, because if the polynomial, the function is a polynomial function, for instance, the derivative is very easy to compute, and the stabilization may come earlier, maybe on the third trial, on the second trial, right? There are a couple of questions related to this when you do homework today, right? But again, when we review, I will try to cover more examples, right? But this is what the Newton's method is all about, right? It's an iterative method that when applied repeatedly, allows you to reach some stabilization, right? And that is when you stop, and this is going to be the 0 of your function, right? This complicated function, polynomial function mixed with this radical function, right? We were able to find the 0 of the equation f of x equals 0 following Newton's method using derivatives, right?